All right, in this video we want to look at continuing to solve for our kinematic coefficients. So what we want to do is we want to eliminate this term, and we'll do that by making it pure imaginary, and we'll do that by multiplying by e to the minus I theta 2. Okay, and so what happens when we do that is this equation becomes e to the minus I theta 2 plus dr2 dr1 plus r2 d theta 2 dr1I, and that's going to be equal to 0. Now, the next thing we want to do is we want to take the real part of that equation, and so that will give us the real part of e to the I theta 2 minus theta 2 is just going to be the cosine of minus theta 2, and then we'll have plus dr2 dr1, and this term goes to 0 because it's pure imaginary. And so what we find is that dr2 dr1 is just equal to minus cosine minus theta 2, which is just equal to minus cosine theta 2. Okay, so that's a very nice expression for that. We can go back to our kinematic equation again, back to this expression right here, and if we take the derivative of that with respect to R3, so what we'll have is we have R1 plus R2 e to the I theta 2 equals R3I. And now if we take the derivative with respect to R3 of that equation, it's very similar to what we just did. We'll have dr1 dr3 plus dr2 dr3 e to the I theta 2 plus R2 d theta 2 dr3I e to the I theta 2 equals dr3 dr3I. Okay, now as we did before, these two are independent variables, so this goes to 0. And then we'll have the thing we're looking for, dr2 dr3 e to the I theta 2 plus r2 d theta 2 dr3, and then we'll have I e to the I theta 2, and that's just going to be equal to I. Now, this is the term we want to find, this is the term we want to eliminate, so we can multiply by e to the minus I theta 2, and that'll give us dr2 dr3 plus r2 d theta 2 dr3I equals I times e to the I minus theta 2. Now, we want the real part of that equation, and so that'll give us dr2 dr3 plus, this term goes to 0 because it's pure imaginary. Now this term looks like I e to the I, okay, and so the real part of it is going to look like minus sine of minus theta 2. And this there's a trig identity that allows us to turn that just into sine theta 2. Okay, and so we get dr2 dr3 is just equal to sine theta 2. Okay, now we can then plug those expressions back up into our expression for virtual work, which we had. So we had dv dr1 is equal to k r2 r2 naught, and then we had dr2 dr1, and we found that was just equal to minus cosine theta 2. And then the other expression we were interested in was dv dr3, and that was k r2 minus r2 naught, and it was dr2 d theta 3, which is going to be sine theta 2. Okay, and so now we can break it for q1, which is equal to r1. We'll have an expression that, or we'll have an equation that says f1 dot dr1 plus f3 dr3 minus dv dr1 dr1 equals to 0. Now this one doesn't have the same dr1, and so what we have to do with that term is we have f1 dot dr1 plus f3 dr3 dr1 dr1, that's just chain rule sort of thing, and then we have minus dv dr1 dr1 equals 0. Now this term we've already talked about. It's actually partial derivatives in here, but it's just equal to 0. Okay, so that term disappears, and so what we're left with is f1 dr1 minus our dv dr1, which we just found, is k r2 minus r2 naught times minus cosine theta 2 equals 0, and there's a dr1 in there. And so if we assume that dr1 is small, arbitrary, but not 0, then we can divide through by it, and that gives us f1 equals k r2 minus r2 naught times that'll give us a minus cosine theta 2.